Thank you. Phobos and Deimos are, of course, quite small. Together, their mass is only about 2 times 10 to the negative 8 times Mars's mass. Their surface spectra suggest compositions consistent with primitive material, or perhaps with space-weathered silicates. Their orbits have evolved substantially over time due to tidal interactions with Mars. Phobos lies interior to the synchronous orbit, which is located at about 6 Mars radii. It has tidally evolved inward substantially over time, while Deimos lies beyond this distance, and its orbit has expanded slightly over time. There have been a number of works of late that have looked at whether these objects could be the result of an impact with Mars. Simulations of impact suggest that they can indeed produce a circummartian disk, and that the disk typically has a mass that's many orders of magnitude larger than the mass of Phobos and Deimos. It's also understood that in order for an impact origin of these moons to be viable, the edge of the disk, the radial scale of the disk, needs to be roughly comparable with where we see Deimos today. If the disk were much more compact, then moons as distant as Deimos would not result. Conversely, if it was more extended, such as the typical disk produced by moon-forming impacts, we would expect to see moons beyond Deimos that would be long-lived, and we don't see those objects. A still open question is whether, if you start with such a disk, can you end up with tiny Phobos and Deimos as the only long-lived survivors? So this is an SPH impact simulation of a impact that has been considered as a candidate by prior works. This is an impactor that has about 3% of Mars's mass, an object with about 20 times the mass of Ceres. And this class of collisions produces disks that have between 10 to the minus 4 to 10 to the minus 3 Mars masses. And I'll call this a massive disk. So we've been exploring how such a disk may evolve. And to do that, we apply a hybrid model that describes the orbiting material inside the Roche limit analytically as a continuous disk that spreads radially due to collisions among the particles in the disk. We describe material orbiting outside the Roche limit by an N-body simulation that tracks the mutual interactions, collision, and the growth of moons. There's mass exchange between the two disks. As the inner disk radially spreads beyond the Roche limit, we remove material from the disk and add it to the outer portion of the code in the form of newly spawned moonlets. As objects in the outer disk stray too close to Mars, we assume they're tidally disrupted, and we add their mass and angular momentum to that of the inner disk. We also include gravitational interactions between the outer moons and the inner disk. These are resonant interactions that lead to positive torques on the moon orbits. They cause the moon orbits to expand, and a negative torque on the Roche interior disk. And if that resonant torque is strong enough, the outer moons will actually shepherd the outer edge of the inner disk to within the Roche limit. Finally, we include tidal evolution of moons as they're growing. Objects inside synchronous orbit tidally evolve inward. Objects outside that orbit tidally expand. This is one of our simulations. So the orange bar is going to show the inner disk as it viscously spreads and accretes mass onto the planet and spreads beyond the Roche limit. You'll see that line drop, the total mass drop. These are the objects in our outer disk. The horizontal line for each case will be proportional to an object's eccentricity. Once I have them start the animation, it'll evolve very quickly. What you'll see is in less than 1,000 years, moons much more massive than Phobos and Deimos form in this region. And they rapidly destabilize and sweep up all of the material that lies in the region where we think Phobos and Deimos began. So if you could start the animation. Could you start the animation, please? There we go. So there's the inner moons. They've already cleared out all the material in this region. And now the system enters a cyclic phase whereby large moons form, they're tidally evolved inward, they tidally disrupt, the disk inside the Roche limit spreads back out, it spawns new moons. But as this cycle repeats, as the disk dissipates, we never end up with a surviving moon outside synchronous orbit. And we've completed a very large number of these simulations, and we find that so long as the disk mass is above about 5 times 10 to the minus 5 Mars masses, we never have surviving Deimos analogs. So because of this, we've been exploring a different regime of parameter space. Namely, we've been looking at lower mass disks to start with. This is the same type of simulation, only now the initial disk mass is an order of magnitude smaller. In this case, the moons that form in the intermediate region are smaller. They have a less destabilizing effect on the Phobos-Deimos region. We also consider strong tides, so that these intermediate moons tend to get pulled inward due to tides rapidly. The combination of these effects allows Phobos and Deimos type analogs that formed initially near the disk outer edge to ultimately survive. And we find that so long as we start with a disk mass of less than about a few times 10 to the negative 5 Mars masses, and if tides on Mars are sufficiently strong in the time period just after the Phobos-Deimos forming impact, we can leave Phobos-Deimos type analogs. So the next question is there an impact that can give us a disk like this, namely with this low mass and with an outer edge near 7 or so Mars radii consistent with Deimos? This is a SPH simulation of a much smaller scale impact. So here we have a Ceres-sized impactor. Could you start this animation, please? So with essentially an order of magnitude smaller impactor, you produce disks that have a favorable total mass for forming Phobos and Deimos. So that's a good result. The challenge here is that this disk mass is very small. This SPH simulation had more than 1 million particles. That's a high-resolution simulation, and yet we've resolved with this simulation the material that goes into the disk with only 80 particles, and each one is more massive than Phobos and Deimos. So while this resolution is good enough to tell us the total mass of the disk, it's not good enough to give us the radial distribution of the mass, and in particular, it's not good enough to tell us where that outer edge of the disk is, which is a key constraint. To address that, we've developed a new SPH code that includes particle splitting. The idea is straightforward. Essentially, you identify a region of the simulation where you desire a higher resolution. And in that region, you replace each SPH particle with a distribution of smaller mass daughter particles. And this allows you to get local order of magnitude increase in resolution. Now, splitting techniques have been used in SPH in astrophysical calculations before that use ideal gas or polytropic equations of state, but their incorporation in planetary collision simulations, which had not been done before, proved considerably more challenging. Nonetheless, the effort was successful, as I'll show you. Our basic approach is that we start by running a standard million particle simulation like the one I just showed you. We use the results of that simulation to tell us the region of the colliding objects that are going to supply the ejected material. We split those regions with finer resolution particles, and then we rerun the simulation with the split particles in place. So this is an example of the same impact of a Ceres-sized object with particle splitting. With this technique, we're then able to resolve the orbiting particles by more than 800 SPH particles. This allows us to get the radial mass distribution of the disk. And in this case, we have an outer disk edge at 8 Mars radii, so at a good position. We've completed 10 of these simulations, including splitting, and we're finding disk outer edges between 5 and 8 Mars radii. So that's very favorable compared to the position needed to explain Deimos. So I think we have the first complete model for an impact origin of Phobos-Deimos. The successful cases apply or are found across a relatively wide range of impact velocities, impact angles. They have characteristic outer edges near 6 Mars radii. And interestingly, most of these impacts produce a disk that originates primarily from material that came from Mars rather than from the impactor. And so this is different than typical moon-forming impacts in which the disk is derived predominantly from the impactor material. One of the key implications of an impact origin that we've heard mentioned earlier in this meeting is that it implies a dry composition for these moons. Specifically at these impact energies, hydrogen species in the colliding material will be vaporized. As the ejecta cloud expands past about 6 Mars radii, which happens relatively early in the collision, molecular vapor has a thermal velocity high enough to directly escape. The thermal velocity becomes comparable to the local escape velocity. So if Phobos and Deimos form by impact, then we would expect their bulk compositions to be extremely hydrogen poor, and that any hydration that we see in their surface layers would be at a level associated with possible exogenic contamination after their formation. And this might contrast substantially with what we could see if they were captured objects, for example. If they were captured, then they could potentially have water-rich interiors. And as we heard about on Tuesday, extremely exciting development is JAXA's plan to fly the MMX mission. It's going to allow us for the first time to probe and really see the subsurface elemental composition of these bodies, as well as the sample return. It seems that this should allow a definitive conclusion on how these objects formed, which will provide an important new constraint on what the dynamical environment was like in this region of the solar system near the end of Mars's accretion. Thank you.
Questions?
Quick question. Does this scenario lead to any prediction of any differences between Phobos and Deimos in composition, for instance?
They should have comparable bulk compositions in such a model. There are not appreciable changes in the disk composition between the distances where Phobos and Deimos would form in this model. If they form by separate capture events, in contrast, they might have different bulk compositions from each other.
The difference in prediction between capture and your impact and then subsequent accretion of hydrated material from outside is a quantitative one. Because even if you capture something, you're going to have some debris knocked up from Mars that will be processed, that will hit Phobos and Deimos. It'd be a tiny amount. If you looked really inside the bodies and had a bulk composition, that would be great. But how are you going to do it from soil samples? Because you're going to get a mixture regardless.
It's true, although interestingly, the estimates of the fraction, the mass fraction of the regolith of Phobos that would be Mars ejecta, it's extremely small. So this is Chapats et al. And Ramsley and Head. This is 0.01% by weight of the regolith of Phobos that would be Mars material. So I think actually that would be a quite minor component of the Phobos composition. It's a much smaller fraction for Deimos, of course, even less. Yeah. So I think a more relevant issue that was discussed in Pascal Lee's talk is the possible transfer of Deimos ejecta to Phobos, which could well be depositing material on the far side, the non-Mars side of Phobos. But at least based on the calculations that are out there, the fraction of Mars ejecta that's in Phobos' regolith is extremely small.
So you're saying that there will be a substantial fraction of Mars material, processed, heated material, assuming the impact model.
Exactly, yeah.
So is there a class of impact scenarios in which the bulk load disk comes from the impactor that would jive a little bit more with the remote spectroscopic analyses of Phobos and Deimos?
The combination of requiring a relatively low mass disk that has an outer edge near Deimos is pulling us into a somewhat higher impact velocity regime that tends to give you a more target-dominated disk. There are some cases where the Mars contribution is as low as 40 or 45%, but
still a lot. Yeah.
It's still substantial.
Yeah.
And there are cases where it's as high as 75.
Wow. Okay.
Yeah.
Just to follow up on that.
Quick.
Yeah. How much does it matter? Isn't even if it comes from the impactor, it looked like it was heated to high enough temperature, as you say on your slide, that it's going to lose its water and not going to look like.
Well, it doesn't matter in terms of water, but if you're looking at a refractory, for example, what you want to look at is to see whether that refractory looks like Mars, because if it does, that's a sign of an impact origin.
Let's thank the speaker one more time.
Thank you.